So our first lab is the lab on constant velocity. So the purpose of the lab was to track and analyze the motion of an object with constant velocity. So we recorded an object moving with a constant velocity, and we used Tracker to track the position over the time. And using the data from the tracker, we built a computational model to plot the predicted motion, the theoretical motion. And then we used the observed data from Tracker to plot the actual motion. So the motion can be described by Newton's second law, which is force equals mass times acceleration, or in other words, force equals the change in momentum. And so this means that any sort of force will create a change in the momentum and therefore a change in the velocity because our mass is constant. And we can derive this Newton's second law formula into position update formula and the velocity update formula, which were the two formulas used to build our computational model. So the result was the observed motion deviates slightly from the theoretical motion because the object didn't have a perfectly constant velocity. So this is a video of the motion that we were observing. And here the system is an expo marker and the surroundings are Earth and the whiteboard slash table. So for our computational model, we set the initial conditions to match the observed data. So the initial position was at the origin, and the initial velocity was equal to the average velocity, because considering that we're trying to plot the predicted motion of constant velocity, our average velocity is going to be equal to the initial velocity, which is also equal to the final velocity. So to get this average, I took the final position minus the initial position divided by change in time. And then to update the position to get the position over time graph model, I used the position update formula where I added the position at the previous time step to the constant velocity times the change in time from the last time step to the new current time step. And didn't need to update the velocity because the net force is set to 0 because it is a constant velocity. There should be no net force, or a net force of 0. So this is the computational model, and we showed the position versus time graph to show how it's increasing at a constant rate. So that slope is constant, the velocity is constant, and this velocity versus time graph shows this as well because it's a straight line throughout the entire time period. And so the theoretical versus the observed motion graph shows that the orange is the theoretical and the blue is the observed. And so it shows that the average velocity is the same because it has the same initial and final position and it's over the same time period. However, the velocity is not the same over the whole time because the blue begins to curve away from the theoretical motion. So this shows that the theoretical motion is constant and the observed motion is slightly non-constant. So possible errors that could have created this are the expo marker being not perfectly round, like the cap shape is ridged and the mass is not perfectly distributed. And also the surface of the whiteboard is not completely frictionless. And finally, the point of mass was manually tracked at each time interval. So when I was tracking each point of mass on Tracker, I may have been slightly off. And so what if the x positive axis was flipped to x negative? So there would be a different direction of velocity, but the same magnitude, because this would just be switching the direction. It would make the x component of the velocity negative because we're swapping the plotted points of x. So this would also create a negative slope for the position over time graph, yes. So, and can you say how many forces are being added together to make net force equal 0? And yes, because we know that there's only net force in the y component because there's nothing pushing or pulling against it in the x component. So we know that gravity is constantly pulling down on the expo marker, and as the expo marker is constantly coming into contact with the whiteboard, then there's a constant normal force of the whiteboard pushing up on the expo marker. So these two vertical forces counteract to make a net force of 0. And in conclusion, the computational model predicts motion of the marker well. However, the observed data graph still curves slightly away from the theoretical motion graph because the real world creates an imperfect scenario where velocity isn't completely constant because there must be some sort of net force that is not actually equal to 0 because any sort of force will create a change in the momentum, and therefore a change in the velocity according to Newton's second law. So we know that for there to have been a slightly non-constant velocity, there must have been some sort of net force or force acting on the marker that wasn't canceled out.